We begin this lecture by a design problem. Okay, so design the circuit whose topology is given below. Okay, to have the also given Bode plot, asymptotic Bode plot for the gain. Okay, so the circuit that we are asked to design has the following topology. An operational amplifier, minus, plus, and this is grounded. So here we have the input voltage that's being applied to the circuit, and this terminal is where we collect the output voltage. So this is R1 and C1, and these are labeled as R2 and C2. Of these four parameters, 2 resistances and 2 capacitances, only the capacitance of the first capacitor is given, and it's given to be 0.5 microfarads, whereas the remaining 3 parameters, R1, R2 and C2, are to be determined. And how we determine them? We figure them out so that the Bode plot, the asymptotic Bode plot for the transfer function from the input voltage V in to V out is okay. It's given here. Omega radians per second. Hj omega gain in decibels. So this is 32, this is 20 decibels, and these frequencies are 200 and 800. Okay, so what we see therefore is it's constant up to 200 radians per second, and it's also constant after 200 radians per second, and in this range from 200 to 800 it decreases with a slope of, so here we have 12 decibels, and here we have from 200 to 800 we go 0.6 decades, so 12 over 0.6. Here the slope is minus 20 dB per decade. Okay, so we will try to now realize the realize our design through the following constraint. Okay, design constraint. We will choose R1, R2 and C2 values so that the corresponding transfer function will produce the following asymptotic gain plot. Okay, so the first step seems to be obtaining the transfer function in terms of our parameter values. So let's do that. Okay, so let's call this combination, or let the impedance, the equivalent impedance of this combination be denoted by Z1, and likewise we're calling this Z2. Okay, so what we have is V in over Z1 plus V out over Z2. Okay, So if you write the node equation, the KCL in this node, this is op-amp, there's no current escaping to the op-amp from this wire, okay? Therefore, the current in this direction plus the current in that direction must sum up to 0, okay? Now, since the op-amp is in linear region, otherwise it wouldn't make sense to talk about a transfer function. Since the op-amp is in linear region, V plus and V minus voltages, they are the same. V plus is grounded, okay, plus terminal. Therefore, this behaves like a ground, okay? The voltage of this node is 0. Therefore, this current is V in minus 0 divided by the impedance in between Z1, okay? And this current is V out minus 0 divided by the impedance in between, which is Z2, and by KCL, that sum equals 0. And from that sum, from that equation, we directly obtain the ratio V out to E in, which is the transfer function. Okay, so H of S, the transfer function, must therefore be equal to minus Z2 of S over Z1 of S. That is, H of S equals minus R2 parallel with the impedance of the capacitor, which is 1 over C2 times S. And as for Z1, we have R1 connected in parallel with the impedance 1 over C1S. Okay, from which we obtain H of S equals minus R2 over R1 times R1 C1S plus 1 over R2 C2S plus 1. Okay, so that's our transfer function. Now, once we have the transfer function, we can figure out the constant term and the first order terms. And we know when the first order terms become active by looking at the Bode plot. We also see what the constant term will produce. And by comparing the transfer function and the information coming from our Bode plot, we will be able to easily figure out the missing parameter values. Okay, so having obtained the transfer function, let's write down Hg omega, the magnitude of Hg omega in dB in terms of our parameter values. Okay, so Hj omega magnitude in dB equals 20 log R2 over R1. Okay, so it's due to this term here, and then we have 1 plus S over 1 over R1 C1, okay, and that produces 20 log 1 plus J omega over alpha, and in this case alpha is 1 over R1 C1, okay, 1 over R1 C1 magnitude. And then we do the same thing for the term in the denominator, and that produces minus 20 log 1 plus J omega over R2 C2. Okay, and then previously what we did, we drew the individual terms separately, and then we combined them, we summed them up to obtain the overall Bode plot. Now we're doing, in a sense, the reverse operation. The sum is given, and from that sum, from that result, we have to see the constituents, okay, the parts that it's made of. So this can be written as sum of 3 terms. First, we have a constant term at 32 dBs, okay, and it's produced by this guy here. So this must be 32 dBs, and then we have a first order term, okay, that's active, that becomes active at 200 radians per second, okay? 200 radians per second. And then this negative slope must be cancelled by some positive slope, and that means we must have a third term, okay, that becomes active at 800 radians per second, okay? Now, since the slope is positive for 800 for this guy, that should correspond to this thing here, and we have 20 log 1 plus j omega over alpha, where alpha is 800, okay? Once again, this is the 800. This corresponds to the pole at minus 800, because here the sign is positive, or this term appears in the numerator. And we have for 800 the positive slope. And what remains is only this guy, okay, and that must be represented by the last term, minus 20 log 1 plus j omega over alpha 2, and alpha 2 is 200, okay? So what we have obtained therefore is 1 over R1C1 must equal 800, 1 over R2C2 must equal 200, and 20 log R2 over R1 must be 32. So we have 3 equations, and C1 was already given, so we have 3 unknowns, so we have what we need. So let's proceed with this solution. We have 1 over R1 C1 equals 800. Okay, C1 was given, so R1 equals 1 over 800 times 1 over 2 times 10 to the 6, because C1 was 0.5 microfarads. And this produces 2.5 kilo ohms for our first resistance. Then we move on to figure out R2. 20 log R2 over R1 equals 32. That means R2 over R1 equals, now log R2 over R1 equals 32 over 20, which is 1.6. Therefore, R2 over R1 must be 10 to the 1.6. Okay, and that's about 40. Hence, R2 must equal R1 times 40. R1 was 2.5 kilo ohms, so R2 is 100 kilo ohms. And the last thing that remains is the second capacitance value, C2. And for that, we use this information, namely 1 over R2 C2 equals 200. 1 over R2 C2 equals 200. We know what R2 is, so C2 equals 1 over 200 times 100,000, okay, 10 to the 5. And that's 50 nanofarads for the second capacitance. Okay, now so far, when we talked about the Bode plots or the transfer functions for which we obtained the Bode plots, we haven't yet talked about the so-called second order terms. So let's also say a few things about them, how to deal with them, or what to expect from them. Second order terms, sometimes also known as quadratic terms. Okay, now what we mean by them is complex zeros or poles that are part of our transfer function. Complex poles or zeros occur in conjugate pairs that appear as second order terms of the following form. Okay. S squared plus 2 alpha omega 0 s plus omega 0 squared. Here alpha is strictly less than 1. If it's greater than or equal to 1, then this can be written as product of two first order terms with real roots, okay? And then when that's the case, we already know how to deal with them. So we can treat this as two separate first order terms. But when alpha is strictly smaller than 1 and alpha is positive, so when alpha is between 0 and 1, then we have to treat this as a whole. We cannot separate it into two first order terms. Example, for instance, take h of s equals 3s plus 3 over s squared plus s plus 2. Now this second order polynomial that appears in the denominator has a complex conjugate pair of roots. Since the roots are not real, we have to treat this as a single piece, that second order term. And as before, what we do is we write things as 1 plus something, both for numerator and denominator. And in this case, we have 1 plus s over 3 as before for the 0 at minus 3. And as for the denominator, we write it as 1 plus something. So that means we take this 2 out. So we take 2 out and we take 3 times 3, 9 out, and that produces 9 over 2. And in the denominator we have 1 plus 1 over 2s plus 1 over 2 s squared. Okay. Now, generalizing this simple example motivates us to consider the following structures. Okay. The second order terms introduce gain and phase terms of the following form. As for gain, we have 1 plus 2 alpha over omega 0 s plus s over omega 0 squared. Okay. It's plus 1. Okay. If it's in the numerator, it's minus 1. If it's in the denominator, namely 1 over that. And then you plug in s equals g omega and you convert it to dBs. That produces plus minus 20 log 1 plus j 2 alpha omega over omega 0 minus omega squared over omega 0 squared. Okay, so we have to deal with such a structure when we're dealing with when we're trying to sketch the gain plot. As for the phase plot, one plus j, excuse me, 1 plus 2 alpha over omega 0 s plus s over omega 0 square. And then we're dealing with the gain of this. It's plus 1 if it's in the numerator, minus 1, or 1 over that if it appears in the denominator. And we evaluate that at s equals j omega. And that means we're dealing with plus for the numerator guy and minus if it appears in the denominator, the phase of 1 plus j 2 alpha omega over omega 0 minus omega square over omega 0 square. Okay. Now the question is how to approximate these terms. Okay. So we again we want to make use of some asymptotic approximation when we sketch the Bode plots for the corresponding terms. Now, the way to approximate those terms is the same, more or less, as how we approximate the first order terms, but the approximation is not as good because we have now complex conjugate roots. Okay, so this is how we approximate the gain. Okay, gain at low frequencies is approximated by the following expression. Okay, so what we do is we, in a sense, ignore this term in the middle, okay, which may not be a very good idea around at some frequencies, especially when alpha is small, okay. But there are many cases where that's a good approximation. So ignoring this, in a sense, produces the following at low frequencies, by which we mean omega less than omega 0, okay. When omega is less than omega 0, then this is gone, that's gone, and what remains is 1. So what we're talking about is 20 log 1, which is 0 dB. Okay, the gain is approximated by a constant, a 0 dB line. That's our low frequency asymptote. And for frequencies larger than omega 0, this time this is the dominating term, so we ignore this and that, okay. And what we have is 20 log omega square over omega 0 square, okay. And that means we have plus or minus 20 log omega over omega 0 square, okay, which equals plus minus, this 2 can be written here, can be put here, transferred here, so 40 log omega over omega 0. It's plus if it appears in the numerator, and it's minus if the term appears in the denominator. Okay, so basically our approximation is such that, or asymptotic approximation is such that for low frequencies, and by which we mean frequencies less than omega 0, we have the 0 dB line, just like the first order case. And for high frequencies, when omega larger than omega 0, we have a constant slope line. Again, like in the first order case, the difference with the first order case is that for first order case we have 20 dB per decade slope, or minus 20 dB per decade slope. This time we have twice that, okay, 40 dB per decade or minus 40 dB per decade, depending on whether it's in the numerator or denominator. So we have the following result: omega over omega 0. This is 1, so this represents the frequency at which omega equals omega 0. And this is the 0 dB line, and we have 1 plus j 2 alpha omega over omega 0 minus omega square over omega 0 square in dB. Okay, so we're dealing with a term in the numerator. So here we have the low frequency asymptote, and here we have the high frequency asymptote, a constant slope line. The slope is 40 dB per decade, okay, because when you move omega from omega 0 to 10 omega 0, let's say, log 10 is 1, so you have reached the quantity of 40 dB. So at every decade, you rise 40 dB. That's why the slope is 40 dB per decade. Okay, now that's the asymptote, high frequency asymptote, and this guy is the low frequency asymptote, and that's our approximation. Now, how about the actual curve? Okay, compared to that approximation, it depends on the actual curve or how far it is from the approximation or from the asymptotes. Depends on the damping factor alpha. When alpha equals 1, okay, that's the smallest alpha where we can express the second order term as product of two first order terms with real roots. This is more or less how the actual curve looks like. So this is alpha equals 1, let's say. And then for smaller alpha, after a while, the curve starts lying below the asymptotes, and we have things like this. Okay. And if you lower alpha towards 0, what happens is this peak reaches minus infinity. Okay, so this is, let's say, for alpha equals 0, and this is, let's say, for something close to 0, let's say 1 over 5. So that means if alpha is tiny, then especially around frequencies where omega is omega equals or around omega 0, then the approximation, the asymptotic approximation, is not that good. Okay, the actual curve is significantly far from the asymptotes. But if alpha is reasonably close to 1, then asymptotic approximation is a good approximation for many applications. Okay. Okay, so let's put that down as a remark. Generally speaking, the asymptotic gain is within plus minus 3 dB of the actual gain. Okay, for 0.3 and 0.7 for alpha, okay, in this range, 0.3 to 0.7. Okay, let's also talk a little about the phase. Okay, so this guy. Okay, so phase at low frequencies, and by low frequencies we mean the same thing. What we meant when we're talking about the phase for the first order term. Okay, as far as the phase is concerned, by low frequencies we mean frequencies less than omega 0 over 10. And then in such frequencies, the phase can be approximated by a 0 degree constant line. And phase at high frequencies. Okay. Now at high frequencies, when omega is larger than 10 omega 0, this time this term is the dominating term. It's negative, it's real, therefore its phase is 180 degrees if it appears in the numerator, and minus 180 degrees if it appears in the denominator. Okay, so that means the phase is plus or minus 180 degrees. Okay, at high frequencies. And then in between, as before with the first order terms, the approximation is such that we connect those two constant lines with a straight line, and the slope will be 90 degrees per decade. Okay. For intermediate frequencies, omega 0 over 10 omega and 10 omega 0, we use the straight line approximation. Okay, whose slope is 90 degrees per decade, plus minus 90 degrees per decade. So it's plus 90 degrees per decade if the term appears in the numerator, and minus for the denominator. So overall, this is how the phase plot looks like. 1 plus j 2 alpha omega over omega 0 minus omega square over omega 0 square. This is the 0 degree axis line, and let's mark this point as 1, and here we have 1 over 10. That is, this corresponds to omega 0, and this corresponds to omega 0 over 10. And then go 1 decade to the right, 10, and this corresponds to the frequency where omega equals 10 omega 0. Okay, now the approximation that's described here is such that it's constant until omega 0 over, until omega equals omega 0 over 10. And it's also constant after frequencies omega equals 10 omega 0, and it's constant at 180 degrees, and in between the intermediate approximation, or the approximation for the intermediate frequencies, is a straight line that connects those two endpoints. Okay, so we have the following, where we at omega equals omega 0 we have 90 degrees of slope. So that's the approximation or the asymptotes. Now how about the actual phase curve? Again, how far the actual phase curve from the approximation depends on the damping factor alpha. Okay, if alpha is, let's say 1, then we have something like this. Okay, and when for small alpha it goes to the other side, the curve goes to the other side, and we have things like this. And as you decrease alpha further and further, as alpha approaches more and more to 0, the phase becomes more and more like step-like. Okay, so this is, let's say, for alpha equals 1 over 5, and for alpha equals 1 over 10, it's more steep, and so on. Alpha equals 1 over 10. And it's not difficult to see that if you set alpha exactly to 0, then you go at 0 degrees until omega equals omega 0, and at that part, at that frequency, omega equals omega 0, when you pass to the right of that border, you automatically become 180 degrees. Okay, so it's exactly step like when alpha equals 0. So in that case, we're very far away from the actual curve with our approximation. Okay, so this is the asymptote, and here we have also the asymptote, and the other things are the non-straight lines are the actual curves. And also the first one we drew was corresponding to alpha equals 1.